And then I introduced the background of my research. So firstly, the most serious barrier of the spreading wireless sensor networks is the battery replacement cost. So considering the problem, our approach is using ambient RF energy harvesting, such as the TV signals. So we use rectenna for RF energy harvesting, and it is composed by the antenna and the rectifier, and it works as a converter from the RF signal to DC power. The fabrication cost of the rectenna is much cheaper than the solar cells, and it can collect 40 to 60 microwatts from the TV signal at the 6.5 kilometer far from the broadcasting tower in Tokyo. So ambient RF harvesting provides a sustainable operation and without batteries. So the TV signal power is spread widely in the urban area. So this map is in Tokyo, and that can be used for the energy source in the urban area. Okay, and this is the measured data of the TV signal at my lab, and then it have some characteristic of this one. So firstly, this radio wave has the short-term variation and the long-term transition. So the short-term variation is coming from the noise and the fading. So it harms the stable operation of the harvested and the sensor node. And on the other hand, so it also has a long-term transition. It's caused by the broadcasting schedule and the facility maintenance. So we are not a broadcasting provider, so it is unpredictable. So this is one case. So some channel is turned off at the midnight, and then this harvestable power is down. So the channel power has mainly two states in this case. So state one is the daytime. So the harvested energy, and this is a histogram of the TV channel. So the purple one is state A. State A means the power in the daytime. So the energy is harvested energy is large, but its deviation is also large. And blue one is at the midnight. So in the midnight, the energy is small, but also deviation is small. So if I want to use the ambient RF energy harvesting, energy management is needed to get robustness to the channel power changes. Okay, so nextly I introduce my proposed method, duty cycle control for the energy harvesting. So our challenge is that available power by ambient RF energy harvesting is quite extremely low and unstable, as I introduced. So considering the problem, we tried to optimize sleep time control to maximize the cycle. Unfortunately, there are two contradictory requirements, and it makes this problem seriously difficult. And when the sleep time is too long, the capacitor leakage becomes larger, and this is significantly large compared to the harvested energy. On the other hand, and sleep time is too short, MCU will be turned off, and due to the energy shortage. And after MCU dead, MCU needs 5 times larger energy from sleep to active mode and sleep from off to active mode. So this should be a problem. So we introduce it in detail. So our system actually is using capacitor as energy storage. So capacitor has a lot of advantages than the rechargeable battery like Li-ion batteries. So capacitor can charge and discharge efficiently and rapidly. Moreover, its charge and discharge cycle is unlimited. However, it has a serious problem that its leakage is quite large. So this is one case that we use the 100 microfarad chemical capacitor, and the DC leakage became almost 12 microwatts. So as I introduced, the harvested energy is 50 microwatts, so it's relatively large. And so the leakage loss is not negligible in this system. Okay, the next. So as I introduced, so MCU dead will harm the energy efficiency of the sensor node. So how to calculate the dead risk of the MCU by energy shortage? So harvested energy from the ambient RF energy is has the variability. So we use the assumption that it depends on the normal distribution, and this is the CDF of the normal distribution. So if the battery stored energy level change is overcome the energy is stored, so the MCU will dead. So it represented by this formula, and finally is the cost function of the dead risk is like this one. So the stored energy is too small, so the risk of death is increasing, and then finally the energy cost is increased. So after that, and we aggregate these two functions. One is a leakage, and one is represent leakage, and another one is represent the dead risk. So these two we add to these two cost functions to make aggregated cost function. So the green one is the aggregated cost function. And then we define optimal stored energy level as it minimizes this cost function. So the orange line is optimal stored energy level. We should sustain this level to operate system efficiently. So as I introduced, so the TV channel has a two state. So this cost function is should be adapted to this state on each state. So the state A is the deviation is high, so it depends on the variance of the harvested energy. So in this case, the dead risk is increased, and aggregated cost function became like that. So at the midnight, the harvested energy is short, but the variance is also short, also small. So the aggregated cost function like this. So deviation of the harvested energy affects the dead risk, and the aggregated cost function is some kind of function of the harvested energy variance. So I go to the evaluation, and firstly, so I show you the prototype of this system. The first one is using the dipole antenna printed on the paper. We call it a paper antenna. And it can catch TV signal and convert energy in the discharge pump to the DC power. And then the sensor will periodically wake up and sense it. So as a result, our sensing interval is 40 to 60 seconds. So it can be used for the structural health monitoring. The another one we called it, named it SenseSprout. It is its power source is 920 megahertz, and it can detect the rainfall and soil moisture change. So we show you the video. So the left one is the energy source, and we transmitted power in the RF signal. This is a monopole antenna. It catches energy and convert to the powers. So it doesn't contain the batteries. So its root has a capacitive sensor. It can detect the soil moisture change. So if I change the dry to wet soil, so the detect soil moisture change. So this gauge means soil moistures. So next step, so we spray water on this leaf. It also a capacitive sensor is printed, so detect rainfall. So it can be used for the agriculture. So this is one prototype of our system. Okay, next we introduce my evaluation result using the computer simulation. So the simulation condition, so this is the input power is TV and the GSM signal, and then we compare the existing LQ tracking approach, and it tried to sustain same stored energy level, like this blue line. So the proposed idea is adaptively changed, and this optimal stored energy level in each state. So it So it is energy level lower and achieves the leakage reductions. So as a result, and our proposed method achieved 5.6% leakage reduction when we use TB data, and also we reduce 7.0% when we use the GSM power data. Okay, we summarize my presentation. Firstly, we realize perpetual operation of the wireless sensor network using ambient RF energy harvesting. Secondly, we propose optimization method to maximize the usage of the square power. Thirdly, we show you the feasibility by implementation. And in addition to that, our proposed method duty cycle control is applicable to the other energy harvesting source, like the piezoelectric, indoor solar power, and so it can be used for the low power energy harvesting. That's all. Thank you for your attention.